You're good to go. Great. So we have Steve Campbell from University College Dublin. Here it's a great pleasure to have him back. So he's known you to Palermo. He visited a couple of times. So Steve got his PhD in Belfast before moving to taking up a few research positions around the world. So he went to Cork, then Okinawa, back to Europe, which means, well, Europe, what was Europe at the time, which meant Belfast again, before taking up a research position, an INFM fellowship in Milan, and then eventually going back to Ireland actually at the time at Trinity College Dublin, and an SF500 personal fellowship. He then became an assistant professor at University College Dublin, and is now an associate, not yet.
No, as of a couple of, I think,
As of
just
a couple of weeks ago.
Yeah.
Associate professor there, and he leads a team working quantum control, thermodynamics, and a little bit of foundations as well, or at least our neck of the woods sort of foundation. So Steve is an expert in quantum control and techniques to control the dynamics of quantum systems, and today we'll talk about metrology and what's her name? Elsa, yeah. And the connection with letting it go. Right?
Yeah, exactly. Yeah, indeed. Elsa, as I said, has very little to do with this, except I said to a few of you, I was moving home and we were listening to a lot of Disney, and I told my wife the title of my talk, and I was like, "Into the Unknown," and something like that, and she's like, "That's an absolute banger from Frozen 2." So, hence Elsa is here. So we will have no other reference to Disney movies. But yeah, what I want to tell you about today is something that really the hero of the story is George. So he's a PhD student at Andrew Mitchell in Dublin, and then he recently finished, and he's a postdoc now working with us. And his PhD really was all to do with quantum sensing. So we were interested initially in things to do with quantum thermometry with many body systems, and that kind of morphed into, towards the tail end of his PhD, thinking about more general questions about sensing problems, and with a particular focus on multiparameter estimation. So very often, at least my limited experience having worked in quantum sensing problems before, was a lot of the time we look at a single estimation problem. There's some parameter we want to estimate, like temperature or field or phase or something, and then we employ some framework in order to ask about how accurately can we determine that one parameter. Comparatively little, or at least comparatively little that I could ever understand, was done about multi-parameter estimation. There's some stuff out there. We'll see there's a lot of frameworks there, but it had, for my taste anyway, very heavily mathematical, and I couldn't quite penetrate into it. So I think what George did, sort of in the last half of his PhD that we'll talk a bit about today, really kind of, I think, revealed, at least got me up to speed with understanding how I think about multi-parameter estimation problems. So first, we want to have a look at what is the frameworks that we're actually going to go with. So for any estimation or any parameter estimation problem, we think about some sort of estimation theory. And there are, no doubt, multiple different ways you can do it. We will focus in on kind of two closely related frameworks that have been employed, let's say, you open up any of the literature to do it, and depending on which camp you kind of fall into, you'll very often be applying one of these sort of frameworks. So the first one, I think, is what's most often referred to as the frequentist approach. And it's the one that I was first introduced to, and it's the one that I suspect that many of you here will have played about with. And it's based on a very simple metric called the Fisher information. So your basic idea, for those less familiar, is if I want to estimate some parameter, I have to do some measurements. So what I do if I have a quantum system, it's prepared at some scale. So what I want is I've got a probe system and I want to use it in order to estimate something. Let's think about, say, estimating the temperature. I prepare it, and in some state, I do some measurement, I get some measurement outcomes. If it is a good probe, I then can change the parameter I'm interested in, right? So let's say I'm trying to estimate the temperature, so I make a small change in the temperature, and I do the same measurement again. And then I'll get another set of outcomes, some probabilities, right? So I get two probability distributions for measuring the same probe. You're doing the same measurement on the same probe, prepared in the same sort of probe state. If those two probability distributions are wildly different, that probe was very sensitive to that small change in the parameter. How do I quantify how different those probability distributions are is the Fisher information, right? So this is just a metric that takes two probability distributions and tells me how different they are. So in the context of metrology, gives a easy enough way in order to characterize something like the precision with which I can estimate something. Because if I do a measurement, I make a small change in the parameter I'm looking to estimate, and my measurement outcomes are now, let's say, very, very different. Fisher information basically says I look at the difference between these two probability distributions. The bigger the difference, that means it's a very sensitive probe. And then what the Cramer-Arrow bound gives us, so from within this sort of framework, is the Fisher information, or the quantum Fisher information, then bounds the variance over this parameter. So this is essentially the precision with which I can tell small variations in this parameter I'm interested in. I do a bunch of different measurements, I can reduce this variance down. It's like the fundamental bound. Right? For quantum systems, the only difference between what we call classical Fisher information and quantum Fisher information is I optimize over all the different possible measurements I can do. Right? So I pick a measurement strategy. For something like thermometry, for instance, you would do energy measurements. But you could also, in principle, do any other measurement. Right? Anything that gives me some information about my parameter is a useful enough measurement to do. In order for this Fisher information to be the quantum Fisher information, I optimize over all possible measurements, and it is the ultimate upper bound of precision I can get. So far, so good. So far, hopefully, most so well. So I'll just very briefly mention that the closely related notion is then the quantum signal to noise ratio. Basically, just whatever the parameter I'm looking to estimate divided by the variance, which again is bounded by, thanks to the Cramer-Arrow bound, is bounded by something related to this quantum Fisher information. This is a useful metric I find for characterizing how useful a probe is for sensing. Right? Like we said, slightly better, I think, way to characterize how good a particular sensor is. But it's synonymous with the Fisher information. I only mention it here because we will come back to it in a couple of slides. Now, this Fisher information approach, this frequentless approach, is often kind of characterized or considered as being a local approach. And I never really understood what they meant by local, but George has convinced me. In essence, this relies on the fact that you kind of know roughly what your parameter, what the value of the parameter is you want to estimate is. And you're just doing small variations in the region in order to really identify what's the exact value that this parameter takes. Right? So if I'm estimating something in temperature, if my probe is very good for estimating temperature, it should be good in some region. Right? I do a measurement, I'll get some probability distribution. I make a small change in the temperature, let's say, and I get a wildly different probability distribution. This is then a very sensitive probe. It can't possibly be that for all the whole range of the parameters, right? If the probability distribution, basically it has to only, this variation, like the high degree of sensitivity kind of gets into a small parameter region. We'll see how that kind of drops out by the very closely related approach, which is Bayesian estimation. So what the Bayesian approach comes from is basically the tools are effectively the same. I want to estimate some parameter. I pick some measurement strategy. I do measurements. I get a set of outcomes. The probability distribution of those outcomes that I get tells me something about the parameter that I'm estimating. What the difference here, so in the Bayesian approach, I can assume no prior information if I want. And that's kind of the assumption that we make at the start here. It's not required, but it's the kind of most basic thing. You assume I know absolutely nothing about my parameter. So I assume that my knowledge is essentially a uniform distribution, completely flat distribution. And then I do a measurement. After that measurement, I get some outcomes, and I use the posterior distribution, so I use Bayes' theorem to update my knowledge. The outcomes will give me some information that will allow me to start excluding regions, or let's say saying that certain regions of the parameter space are less likely for to be the parameter I'm interested, to be the value of the parameter I'm interested in learning. And then as I do more and more steps of that, more and more measurements, this posterior distribution will converge down ideally to the parameter value that I'm looking for. So these are the two basic camps. You don't need to worry about the specific details of this hugely after this slide. Right? So if I've lost you a little bit, don't worry too much. The important bit is that these two things are closely related by what's called the Bernstein-von Mises theorem, which is basically saying, and this is where I found the global versus, I would say the local versus global kind of picture of these two approaches kind of becomes clearer. In the Bayesian approach, I can have no knowledge whatsoever about what my parameter is, right? I want to estimate the temperature. I have no idea whether or not it's zero temperature or infinite temperature. I do measurements and then I update my information. So my probability distribution goes from flat and then it starts kind of converging into something. As it converges, it will become a Gaussian, and the width of that Gaussian in the limit of a very, very large number of measurements is exactly this Fisher information. And that's the kind of connection between these two. That as I go from zero knowledge at all about my parameter, and as I converge in on roughly where it is and like the variance around it, I recover this low picture of the estimation. As I get closer and closer to what the actual true value of my parameter is, the variance from the approach matches up with what the Fisher information is. That's kind of at least my rough understanding of the global versus local picture. Okay.
All right. Can I, so
Sure.
why don't isn't the method with the Fisher also variation just with a very fixed prior at the end of the day? Or is it frequently instead of variation?
No, I think that is probably right. But how do you get to that kind of peaked prior in the first place?
Yeah.
Right?
And that's assuming that you have a very big prior.
Exactly. If you have a peak prior, you're already at the limit of kind of large measurements here, right? Yeah. Or you've already picked a really good starting kind of assumption. But that's kind of why so I told you I could talk for hours. It's 10 minutes and we're only on one slide one. So, okay. So that is essentially the picture for if I'm estimating a single parameter, right here, I've just picked some random parameter t, right? I talk about temperature, it could be any parameter. But what happens if I want to infer more system parameters? How do these things change? We're going to start with the Bayesian approach because that's simple, right? It's very, very easy. I can take Bayes' theorem here. These conditional probabilities, they don't have to be only based on one parameter. I can have conditional probabilities of multiple parameters. So at the end of the day, it's just a probability distribution that I'm updating. That is easy to do. Fisher information picture, a little bit more subtle, so we need a little bit more machinery to build up. But what happens is this goes from being like a scalar quantity, just a number I'm calculating, to a slightly more object as the quantum Fisher information matrix. So, and we'll see what we're really interested in is what is the connection between these two frameworks whenever we're dealing with these multi-parameter problems. So, okay, let us think about the simplest possible situation that, well, at least the simplest situation that George came up with for a non-trivial, I think, multi-parameter question. So what we're interested in, we're going to assume I have a few qubit system, and it's going to act like a probe, right? Now, you can think about multi-parameter problems, I think, in kind of two related ways. On the one hand, you're really doing a multi-parameter estimation problem. There are two parameters in my problem I want to estimate. I don't know what they are, and I want to use one system in order to determine these two numbers. Think about like a temperature and an applied field, or a coupling value and field, or a coupling and an isotropy, that's the word, is what we're going to look at here. So that's one way of looking at it. The other complementary way is saying I want to estimate a parameter, let's say the field, but I don't necessarily know all of the other parameters in my problem with certainty. And this is kind of the more physically well-motivated situation that is, to a certain extent, less appreciated when in a lot of the estimation theory papers. Like most papers or most studies that think about single parameter estimation automatically assume that you have precise knowledge of all other system parameters, right? If I'm using something to probe anything, I'm using it as a thermometer, I am assuming I know everything else. I know exactly how strongly it's coupling to my system. I know exactly what its energy level splitting is. I know all problem parameters with certainty. That's just not true, right? There's always some degree of uncertainty present. So another way you can think about these multi-parameter problems is kind of putting that sort of hat on. Yeah. So they're kind of synonymous. We'll touch on hopefully both of them if we have time. But for now, let's just think about this as a 2-parameter estimation problem. It's the kind of cleanest way of thinking about it. So what we're going to have is a super simple little 4-qubit spin ring that's defined using this isotropic sort of Heisenberg-like or XY model, right? So there are 3 parameters here that define it, and we're going to use the ground state and say how good a sensor is the ground state of this 4-qubit spin chain as a probe for any 2 of these parameters. And so I can pick 2. So we start off here with, let's say, I want to estimate what the global coupling strength is and what the anisotropy is, right? These are 2 physical parameters of the Hamiltonian, and I want to see how sensitive is the ground state of this probe to these 2 numbers. And I use the Bayesian approach. So it is trivial to extend what we had on the previous case to this approach. So I have just 2 parameters that I put in. I look and I use Bayes' theorem in order to do just the update steps. So we start assuming no knowledge. So both parameters we assume could take any value within their allowed parameter space. So essentially extending out to plus and minus infinity. And okay, the precise measurement that we chose to implement here, I can't remember exactly. I think it was something like a magnetization or collective SX or SZ measurement. Precise details, not so right. What's important is using the Bayes approach, what happens to the probability distributions as I increase the number of things that I'm doing, the number of measurements. If I have a moderate number of measurements, what we already see is as I update my probability distribution, this is the joint probability distribution for what value my probe, what value my parameters are, it starts to exclude big regions of the parameter space, and it starts converging in on what the true parameters are meant to be. Right? So as I do a moderate number of measurements, if I look at the marginal distributions here, they're not Gaussian, but they're not Gaussian, right? They're kind of getting there a little bit. I do a couple of orders of magnitude more measurements, and we see the beauty of the Bayesian approach kind of coming through. What is happening? I started with no knowledge whatsoever of my 2 parameters, and as I do my measurements over and over again, I update the knowledge that I have, my distribution starts converging, I get 2 very nice looking Gaussians here, and it's zeroing in on what the true parameter that I started from. So here, trivial enough case, what you'll also find is that Bernstein-von Mises theorem is nicely satisfied, that the width of this Gaussian is exactly the quantum Fisher information if I were to calculate the quantum Fisher information for either of these 2 parameters of the ground state of this system. Right? So everything sort of sits very nicely. One might say, what's the point? This is almost a trivial problem to do.
But when you update here, is every single measurement, you update the posterior.
Your posterior. And so the posterior of n-1 is then fed into the nth measurement item. So
this is the quantum Fisher information, the classical Fisher information?
I think it's probably the classical Fisher information for the measurement choice. And I think we chose the measurement. I don't know if in this instance the same, I don't think it's the same measurement that saturates the SLD for the two parameters. So I think it's the classical Fisher information probably here. But okay, what happens if we just change the 2 parameters, right? My Hamiltonian is defined by 3 parameters. Now, don't get ahead of me. I know you can rescale this Hamiltonian, right? So later on. But at the moment, imagine this is an actual applied field. This is some anisotropy degree, and this is some global coupling strength. We saw Bayesian estimation very nicely converge to the point to exactly the 2 parameters. Had I moved my 2 true parameters to anywhere else in the parameter space, it still works. It still would have converged to exactly what those numbers were meant to be. If I do it now for these 2 parameters, Bayesian shows me something very, very different. So after a moderate number of steps, fine. I haven't done anywhere near enough steps for it to converge, so I get this kind of general behavior. It's excluding big regions, but there's a kind of line of persistent likelihood that kind of stays there for some reason. And then I do another couple of orders of magnitude where I know in the first case, where that almost completely converged to exactly the right points, that it converges down onto this line of persistent high likelihood. The marginals are meaningless here. They're not telling me anything. They're not Gaussians. There's no obvious relationship here between my Bernstein-Von-Mises theorem and the frequentist Fisher information picture and what the Bayesian thing is telling us. It's telling us something, but it's just not exactly converging to, in this multi-parameter case, it's not converging to what we would expect. So what is it that this is telling us, and how really sort of important thing is, if I take this same problem and ask the frequentist picture, the Fisher picture, what does it tell us here? Okay. So far everyone's still sort of relatively with us? Okay. So we want to look at the multi-parameter version of the frequentist picture of the Fisher information approach. And so as I said at the start, that requires a slightly more sophisticated modification of the framework compared to, I think, the Bayesian approach. Bayesian, you just take the probability distribution and add an extra parameter to it. For the Fisher information, well, we have to upgrade our Fisher information from a scalar quantity, from just a number we're calculating related to a single parameter, to a Fisher information matrix. Right? So it will be related to the single parameter sensing that I have, like how accurately can I estimate parameter A and parameter B, but also there's obviously going to be a relationship between those two parameters. They're going to be in some way related, in some way dependent on one another. And the Fisher information matrix allows you to take that into account. So the reason I mentioned earlier about the signal to noise is we got some nice results in one of George's papers during his PhD that we expressed in terms of the signal to noise ratio rather than the Fisher information matrix itself. They are synonymous, but just notationally, this is the multi-parameter signal to noise, right? So what is the precision, if you will, of how well I can estimate two parameters in my problem? I have whatever the two parameters are, so the signal divided by what would be the noise. So in the single parameter case, this would be a number divided by the Fisher information, right? So it's a number divided by a number. That's what this here is. For the multi-parameter case, it's different. I have the two numbers divided by something which is is coming from a matrix. It's the matrix inverse, right? So it's related to the covariance, if you will, between the two parameters. Why this is important, or why I find this very relevant and interesting, is that it's this guy here, which is kind of the crux of everything that I'm telling you about today. When I move to this multi-parameter picture, because I'm not dealing with a number anymore, I'm dealing with a matrix, in order for this to be meaningful, or if you even think about the multi-parameter generalization of the Cramer-Rao bound, Cramer-Rao is basically telling you that the precision, the variance of your parameter, is bounded by 1 over the Fisher information. When I go to the multi-parameter case, my Cramer-Rao bound is still defined, but it's now a matrix inequality. And it's going to be related to 1 over something to do with the inverse of the matrix. And so the matrix inverse, well, if I'm dealing with two parameters, trivially, we go back to our linear algebra. The inverse of my Fisher information matrix is I shuffle the elements around a little bit, and I have the determinant here. And this is the kind of crux of it here. That determinant, if that matrix is singular and the determinant is 0, this is not defined. And that means if I have a singular Fisher information matrix, that frequentist approach to estimation kind of breaks down, because there's no meaningful Cramer-Rao bound. Because if the matrix is singular, I'm basically saying that the two parameters are so interdependent on one another, if I have any uncertainty in one of the parameters, I cannot possibly learn anything about the other one. I have to absolutely know everything about the problem with the exception of the one parameter I'm interested in estimating. That's kind of what comes out from here. So we'll see this a bit more concretely. Because I think this was one of the nicest results that George found during his PhD. That again, for sure, this is in the metrology literature somewhere, right? Very, very smart people have done a lot of stuff with the Fisher information and multi-parameter generalizations, but we couldn't find it anywhere else, so we wrote it on first, or at least first as far as we could tell. But so this is, I think, a really, I think it captures the intuition, but it formalizes it very, very nicely. And if I'm thinking about, I want to do this multi-parameter estimation problem, right? So now, if I think about it, again, remember those two ways I was saying you could think about a multi-parameter problem. If I think about it in the sense of, I want to estimate one parameter, but I don't know all of my problem parameters with certainty, then my estimation of one parameter is impacted by how much uncertainty I have in any of the other Hamiltonian or any of the other problem parameters. And that's what this is basically saying. I want to estimate one of the parameters. Let's say it's the field in my problem. And I have some uncertainty, let's say, in the coupling that's there. This signal to noise can be decomposed into a term which is the ideal situation. So this is estimating single parameter. So how well do I estimate that parameter with this probe system, assuming I know everything else perfectly, minus a strictly positive term, which is inversely related to how well I can estimate the other parameter. So what this is saying is, the better I want to know one of the parameters, the worse I know the other parameter basically destroys it, right? And in particular, if I really know nothing about this parameter, then everything sort of goes up, everything goes. And there's a bit of relationship between like how their interrelation feeds in. Like if the two parameters are completely unrelated, this is basically a correlation term between them. If that vanishes, then I can estimate the two parameters with no problem. But that rarely ever happens. So this is the sort of formalism that we have if we're interested in multi-parameter estimation using Fisher information. So the important thing is, if I want it to be a meaningful problem, I need to be able to compute this object if I'm doing two-parameter estimation, and that involves this determinant. So now let's go back to our simple little silly problem of looking at estimating two Hamiltonian parameters using the ground state of this simple 4-qubit spin ring, and see what happens in the two cases. What I find is that if I compute the Fisher information for the case where I was estimating the anisotropy parameter and the global coupling strength, this is where Bayesian converged to a point. Everything was very nice. And if I compute the Fisher information, the Fisher information matrix, I'll find that this thing is well defined. It has a non-zero determinant, it's non-singular, and so everything sort of matches up very nicely. That we kind of expected. What was more interesting, or let's sort of knock on, is that whenever the Bayesian converged to something that wasn't the true parameters, it was converging to a line of high likelihood, that corresponded to instances whenever the Fisher information matrix was singular. And this was kind of, I think, the nice insight that came from here. That if you only restrict yourself to this frequentist picture using the Fisher information, as soon as you have a singular Fisher information matrix, that's it, all bets are off. You basically are saying, I cannot do any sensing with this probe for the two, let's say for the two parameters I'm interested in, because any uncertainty in one of the degrees, in one of the parameters, destroys any, the ability for me to estimate the other parameter. But if you marry the two between the Fisher information and the Bayesian approach, we see that actually there's something a little bit more subtle going on. That the Bayesian does converge. It doesn't converge to exactly the points, to the exact numbers, but it tells you that there's some sort of functional dependence between the two of them. Like if you look at what happens in Bayesian, the line of high likelihood sits somewhere, and the true parameters you're estimating always lie on this line of high likelihood. So you learn something about what your actual two parameters are, you just can never know what they are exactly. And that corresponds to a singular Fisher information matrix. So the singularity of the Fisher information matrix tells us something kind of interesting about the parameters. In fact, trivially, if you've been looking at this remotely closely, the Hamiltonian we defined, I said earlier, I could easily rescale that Hamiltonian, right? If I'm estimating a field and any of the other two parameters, I could have just divided through my Hamiltonian by the field, I rescaled it, and then I'll get some rescaled parameters, right? What this is telling us, or in fact how we interpret this singularity in the Fisher information matrix, is that your problem is actually over-parameterized. That in reality, while you're doing you think you're doing a two-parameter estimation problem here, you're actually looking for a single effective parameter. And the functional dependence between the two of them is captured by whatever the line of high likelihood that the Bayesian converges to. And that's something you don't get access to from the Fisher matrix, easily at least. So using the two kind of combines them, yeah?
Just one thing. If you have multiple parameters, the number of zeros in your value should give you how many of them are perfectly correct.
Exactly. Indeed. So if you look at your Fisher information matrix, if you look at the number of zeros, tells you, I can't remember if it's the number of effective parameters you have or the, right? I think it's actually, yeah.
The rank should be the number of linearly independent parameters or something.
Yeah. So at least in our instance, like we look at very simple problems. So we do 2-parameter estimation, and so whenever it's singular, we find that there is in fact only one effective parameter. So there's only one zero item.
So here on the bottom right, if you do the marginal in the other direction, you should get back a Gaussian, right? But if you do the thing you did, the top plots, you get a Gaussian with IM.
Yeah.
Now in the bottom right, you do the marginal, but like this direction, you should get a Gaussian again.
Stop getting ahead of me. Of course. Indeed. So we will get to it. You do actually recover, like once you have that single effective parameter and you identify it, you do recover back all of the kind of standard estimation theory, right? And so we'll see a nice connection between Bernstein-von and the Fisher information for the effective parameter. So, now, this kind of got us interested in thinking about the singularities of this Fisher information matrix. So what is it? So we see in a practical instance, or let's say in a sort of simple example instance, that singular implies that the Bayesian will not converge to exact true values, but it'll converge to some line of high likelihood, and on that line of high likelihood, somewhere is our true parameters. So that's the best we can do. So we learned something about what the Bayesian estimation is going to do as a function as reflected in the behavior of the Fisher information matrix, and vice versa. If we have the Fisher information matrix, it'll tell us something about how quickly let's say, what our Bayesian approach will converge to. What's also kind of quite cute or quite interesting is, George looked at a couple of examples here. I can compute this determinant, and maybe that's non-zero. If it's non-zero, then the Bayesian approach will converge to the true values after enough measurements. How many is enough depends on how small that number is. If it's a sensible number, let's say something that like nobody would mix up with being close to zero, it'll converge on the order of, as we saw, sort of like 10,000, 20,000 update steps, you'll get to your true values. If this number is like, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, something like that, you'll find that it will converge, but it'll take orders of magnitude more update steps. Every time you do a measurement, you're getting a very small correction to your posterior. You do get a bit of a correction, and so it will eventually converge, but it gets much harder. So again, something interesting comes out just from looking at the Fisher information matrix. If it is not singular but close to zero, if that determinant is close to zero, you will have to do a crazy amount of measurements in order for your Bayesian estimator to converge. You'll still get there, but it's maybe not practical, right? So maybe you need to find a different measurement approach or a different approach system. But okay, let me tell you quickly. We got very interested in picking apart this a little bit more, and what the guys convinced me of, or say what they went through, is that there's really kind of 3 different instances where that can mathematically at least give rise to singularities of this Fisher information matrix. So there's 3 ways in which we could imagine that this determinant ends up being 0. So we just very quickly look over these 3 instances. So the simplest one, the sort of most trivial one, is the one that we've been looking at, right? If I look at my example Hamiltonian, this is the kind of cleanest way to demonstrate it. I have my 3 parameters that I could want to estimate, let's say, any 2 of. Well, the instance whenever this was singular corresponded to when I was estimating, let's say, lambda and h. It would be singular if I was calculating h and gamma, right? You can check that for yourself. I can obviously though just simply rescale this Hamiltonian, just divide through by h. That won't change anything at the level of what my ground state is. My ground state's dependence is still basically the same. And so that rescaling kind of already tells you that, in fact, there are not 3 independent parameters here. There are at most 2 independent parameters. So in this instance, trivially, for the parameters we were estimating was here, right? There's like a ratio between these 2 numbers. Right? And that's kind of what we see in the line that appears at the high likelihood. That is reminiscent of some linear dependence between the 2 parameters, which trivially comes out here, right, from the rescaling the Hamiltonian. So there is only 2 effective parameters there. So it's a trivial, simple case to see it, but this more generally does happen in more, like we have a couple of more complicated examples in the paper. There is another type of singularity that we call the hidden metrological symmetry. A little bit harder to kind of get your head around, but if you remember what we did in this instance, right? This was a little spin ring, right? So the 4 qubits were just talking about it. If I modify this very slightly by adding all interactions, so I have a few more interactions in my little 4 qubit system, but otherwise it's the same thing. In the ring case, if I was estimating lambda and gamma, the problem was non-singular, right? That's the first example that we looked at. I do the Bayesian estimation, it converges to the 2 true values. If I calculate the Fisher information matrix, it's non-singular. Everything makes sense. I make a small change to my probe system, and I look at estimating the same 2 parameters. In this instance, for this all-to-all connected model, then I end up seeing that the Fisher information matrix is singular. If I do the Bayesian estimation, it will converge again to a line of high likelihood and doesn't converge to the point of the true values. The difference is, I mean, even from here, like up here, we know the reason that lambda and gamma, estimating those 2 parameters, gave rise to a non-singular Fisher information matrix, is because they're not trivially dependent on one another, right? There is no obvious way, or there is no way for me to break up this Hamiltonian, to rewrite it in any way that will write lambda and gamma kind of separately from one another. There's no way for me to do it. You would think, or at least I would have thought, looking at this, by just adding those 2 extra interactions, that not that much is changing. But actually, there is no way for me to break those 2 parameters, or there apparently is some way for me to split those 2 parameters up. So it's not obvious. It's not obvious at the level of the state, but it does happen, right? And in this instance, you can work out what the relationship is. But the easiest way to determine these relationships is just do Bayesian estimation, because it will converge to the line of high likelihood, and that is the functional dependence that the 2 parameters have on one another. So we have some examples where it's highly non-trivial relationship, but it just drops out from the Bayesian estimation. These 2 are what we were referring to as these like metrological symmetries. This is something that's coming from the over-parameterization of the problem. Even if it's not obvious from the outset, it's obvious here, not obvious here, but the Fisher information matrix and the Bayesian approach kind of reveal to us what is happening. There is one more possibility, which is what they call the type 3 singularity, which was a measurement dependence on the effective parameters. So what we know is that these singularities drop out from some sort of relationship between the parameters itself, right? So there's some over-parameterization either at the level of what the state of the probe is, or something a little bit more subtle, but it's still at the level of the state. The type 3 that we call it was at least a mathematical possibility, which is that maybe the measurement I've chosen, the measurement outcomes themselves, have some dependence on these effective parameters. This is something that I think Andrew convinced me is a mathematical possibility, but could not come up with a single example for it. Couldn't find any instance that we could demonstrate this, but at least sure there was a mathematical argument for it. So we have no example of this, except to say that we think it can happen, we just don't know if it ever does. Right? So it's a very, very, very short part of the paper that's kind of right in the middle of it that we just glossed over. So, okay. So, I still have like 5 minutes. So now we have a look at, well, when we get this singularity, we know that it is converging to something. We know that something is related to the Fisher information matrix. The fact that it's singular, we know then if we look at the Fisher information matrix, we know there are some 0 eigenvalues, some non-zero eigenvalues. So we know there is an effective parameter in our problem. If we can identify that effective parameter, do we recover back the sort of regular metrological picture? Do we go back to what we saw before? Do we have a clear relationship between like the Bayesian approach, what it does converge to, and what the Fisher information matrix was telling us? So this is what Luca already kind of jumped ahead to, right? Which is, if I look at my simple problem again, where I know my Bayesian approach is converging to this line of high likelihood, so I know there's some functional dependence of my 2 parameters. It is converging to something, that effective parameter. If I can find out what that effective parameter is, does it respect the kind of Cramer-Mayo bound and the Bernstein-von-Mises theorem and everything? And so the question then is, well, what's the correct reparameterization of this? Right? Because what I know is this is what we call the type 1 singularity, right? So it comes from the fact that I can rewrite my Hamiltonian in some way that reveals that it is not dependent on three parameters, it's actually only dependent on two effective parameters. So once I know that, then I should be able to do the regular estimation theory of it. So again, in this instance, I think it's very easy to see that, exactly as Luca was saying, what if I, instead of calculating the behavior, the marginals along these, let's say the sort of normal picture, I do some reparameterization, I do some rotation, something to my problem. If I look at a reparameterization of this, I can write it in terms of these, let's say these two effective parameters. One, which is completely useless to me, it has nothing to do, basically it doesn't play any role in my Hamiltonian at all. And then this is the actual effective parameter that we are looking at. And if I look at what happens here, this thing starts converging and it converges. So I have no dependence whatsoever on whatever this B parameter is. And the Bayesian approach is converging to exactly a value. And that value is exactly, in this example, the ratio between the two parameters I'm estimating. Right? So it's exactly the functional dependence that I do have access to. And if I look at what happens for this reparameterized picture, this thing, after a sufficient number of update steps, is converging to a very nice Gaussian. And if I take a sufficiently large number of measurements, that Gaussian is exactly the Fisher information for the effective parameter. Right? So once you know your effective parameters, you're back in the game. That everything kind of makes sense. The multiparameter, or the parameter estimation according to the Fisher information matches up with what the misses here, what the Bayesian approach is telling us about. So this is simple. I think it's kind of obvious for the example I'm showing you, but there are instances where it's a little bit more subtle. Like, I think, when I show you this, it's kind of clear that, okay, if I take a cut through basically perpendicular to what this line is, then I will get what the correct effective parameter is, and so it follows on that I'll get exactly the behavior. But if I look at some of the other examples we looked at, like there was another example we did for the Heisenberg chain, I think, where we were estimating like the coupling and some other parameter. And instead of getting a nice line, we got a line that was like squiggling around like this, right? That's the Bayesian kind of converged to something completely weird, but there was a functional dependence, and we were like, well, no way that we can work out what the effective parameter is. There is one, but we have no idea what it is. But if you can do this reparameterization, then you're back in business.
Right, this reparameterization is not linear in general. Like this reparameterization,
yeah,
it's something non-linear.
Yeah, no, absolutely doesn't have to be linear. Like here, I think it's simple.
Right? Yeah, it also spreads. So
actually, because we did another example of this. So we do another parameter. So there's another parameterization where instead of the parameters being like related to in this ratio way, they're kind of related in a product way or something. And what you end up getting is like a banana shape. You do the reparameterization of that, it doesn't match up quite as perfectly.
But is it just a reparameterization, or I have to redefine or to define new operators in the operator part of the electron? So is it some form of weird rotation of my operators so that it looks in this rotated frame, it looks a bit easier?
I think it is just a reparameterization, but that might only be because of the problems we looked at. Yeah, I think if you maybe take a slightly more complicated problem, yeah, I don't know for sure.
Okay.
But is that reparameterization, is it possibly related to the not trivial eigenvalues of your Fisher information matrix? Is there, say, if you have your Fisher information matrix, then you have your parameterization point by point, of course, is not around the whole parameter.
So the hope, or what we initially thought, was that the non-zero eigenvalues of your Fisher information matrix were just your effective parameters. That's what we were sort of expecting.
Yeah, the eigenstates, I would say. So the relation between the ratio between the two parameters are the relative ratio to the component of your eigenstate.
Yeah. Yes. And I think George and Andrew looked at this, and it's not necessary. So it's not as, because I think it ends up being the case here, where like the kind of almost obvious reparameterization of your Hamiltonian from the outset, but for a more complicated case, it wasn't exactly that.
But I mean, it's only in many cases going to be complicated because the feature information is dependent on which area of your parameter space you're looking at. So that's in general it's going to be non-linear. So I don't know whether complication that you see is related with that, or is it some further complication?
Okay, offhand, I don't know for sure. From what we looked at, I think it's more something. I think it's more complicated than that, but I can't say for sure. Okay. So everything we covered up to now was looking at that multi-parameter estimation problem and kind of thinking about it in those two ways you could think about multi-parameter problems. Either I'm looking to estimate two parameters using my one probe, or we're going to focus a little bit more now, or just a couple of minutes. I mentioned the slightly other approach where imagine I want to estimate some parameter and I have some uncertainty in another parameter of my problem, but I don't necessarily know nothing about it, right? Like the previous framework, everything we were looking at there was kind of really assuming I don't know any two parameters I'm looking at. That's in general not necessarily true, and in particular if I'm doing something like looking at these small or even moderately sizable many-body systems as probes. One of the things that the many-body systems, the reason they're useful for as sensors is like if you have critical phenomena, if you're close to a critical point, then in principle, if the parameter you're interested in estimating is sensitive or it can be encoded in whatever the order parameter of your model is, then you get very high sensitivity kind of for free, just from the fact that it's got a criticality there. The issue with those is always that you need to be able to prepare the system close to that value, close to whatever that problem is. So what we were interested in this, let's say, related work was what happens if instead of the sort of traditional multi-parameter estimation, I assume that I just have imperfect knowledge about one of the parameters. So I'm going to be interested in using, again, a many-body system. So take an Ising chain, let's assume neighbor interactions. And I'm going to be interested in, let's say, estimating this field. And I'm going to assume that maybe that I think I know what the parameter, what the coupling is, but maybe I don't know it exactly. If I want this to be a good many-body probe, I need to prepare it close to its critical point, and therefore I really need to know what value I'm sitting at in order for me to have that high degree of sensitivity. One of the problems is like creating these many-body states is very, very difficult, and maybe you're close to it, but maybe you're like a few percent off the value you think. How does that impact the ability for this many-body system to act as a highly accurate probe? That's kind of what we were looking at here. So it's a slightly different view to the multi-parameter problem that we were compared to what we were looking at for this first 45 minutes or so. And so how do we formalize this? How do we do the framework here? Well, instead of assuming that we have no knowledge, we then say, well, imagine that I think the parameter, but there's a bit of wiggle room on either side of it. So how I can model that, or I can build that up, is instead of dealing with the pure states, I assume that, in fact, I'm preparing a density matrix. Right? So I have the parameter I'm interested in measuring, and then this is the control parameter that I have, right? So I think I know what it is, but I allow for there to be some uncertainty, some sort of classical uncertainty around it. So just distribute it according to some Gaussian. What we asked is, well, do you still recover the kind of high sensitivity that these many-body systems are purported to have, even if you allow for this kind of degree of uncertainty? If you allow for there to be some meaningful amount of uncertainty in your control parameter. And the punchline of this was that, yeah, it actually still works, but there's a trade-off, right? That's kind of like, we just focus on these two panels, that if I have a moderate size system, the red dashed line is assuming I know with certainty. I've prepared the state exactly at its critical point, and then I can calculate what my Fisher information is. It will peak around about where the critical point is, which is good if that's the parameter, if the omega is the parameter I'm looking to estimate. And if I do a scaling, if I look at how this scales with the size of my system, I get this n squared scaling, this quadratic scaling. So the bigger the system, I get a quadratic improvement in the precision with which I can estimate this parameter. Now I add this degree of uncertainty, right? So I start saying, well, okay, I'm close to the critical point, but I take this density matrix that's kind of like a smeared out version across the values. And I look at basically the same thing. So as I increase the amount of uncertainty I have, and I look at various different size systems, what I'll find is that depending on how big the system is, how much uncertainty I have, I will maintain this quadratic scaling to a point. And then there's a degree of uncertainty when it'll transition from being a quadratic scaling to a linear scaling. A linear scaling is essentially classical, right? So then like every qubit I add just adds a kind of linear amount more information. So this orange region is kind of where there's a quantum advantage, and then this red region is kind of what you would get with classical resources anyway. And so what we thought was quite interesting, and kind of the main takeaway from here is that even if you have a bit of uncertainty, and you're in this sense, kind of classical uncertainty, I would call it, that there's a trade-off between how big your probe can be and still recover this like kind of quantum advantage, this kind of Heisenberg-like scaling. But at some point that will break down, and eventually you'll end up going just back into linear case. And there's this kind of non-trivial trade-off. So what I think was kind of nice here, because what we started was Carol famously has been sort of trying to shit on all things to do with many-body sensors. She's like, no, like you can't prepare these states, it costs you too much. If you take into account the time resources, these are not good. What we kind of at least established here is that they can withstand a certain amount of noise, a sort of certain amount of imperfection, and still get a advantage demonstrated. So he was kind of a little bit kind of happier with their performance, at least after this. So he's still working on it now. Let me wrap up now, because I think, as promised, I have wrapped it on for a little longer than planned. I talked an awful lot about sensing, and we focused on the kind of fairly simple settings, while it was in sort of equilibrium cases, right? We were preparing the system either in a state there at the end, or density meter or something at the end, or we were just looking at ground state behaviors and just looking at how sensitive or I'm allowed to do some time-dependent manipulations or something a little bit more refined. So I think we already have a little bit of work on this, looking at it in the thermometry, like just literally taking the probe, just firing it into something, just giving things a kick and looking at the dynamics. Super interesting, super fun to calculate. But then also there's other like more, I'd say almost more sophisticated approaches like collision models and sequential things where you manipulate systems to go in contact with whatever you're looking to probe, and you add an extra degree of some sort of control on top of it and ask how accurate can I determine some parameters. So this is kind of some of the stuff that, well, I'd say I will be working on, that George will be working on for the next kind of 3 years, and I will come back in a couple of years' time and take the credit again for it. So yeah, with that, I wrap up and just say, key takeaway is that this object, Fisher Information Matrix, super interesting and tells us something I think very, very relevant about the sensing capabilities. I really liked seeing this connection between when it's well defined, what it's going to show us at the level of the Bayesian statistics, the Bayesian estimation approach, versus when it's singular, something else, something more interesting drops out. But and I think there's a lot of work still to go on in here. So I flash up just to say that, as I said, like George really was the hero of this. It was like most of his PhD work was kind of captured in these couple of papers, where really we looked an awful lot at these multi-parameter problems, and I think wide scope asking a lot more questions. So with that, 55 minutes. I will stop there for now, and thank you very much. I'm around for the next 2 days, so feel free to come by and just.
Thanks, Steve. And I forgot to mention that some of the speakers have been published in an awesome journal.
Indeed.
Questions?
Can I ask you again, can you say a few more words about how the parameterization works there? Like the reparameterization to find correct the parameters?
So
How do you actually find those?
How do we do this one?
It's not going to let you.
I know, well, I'll just put you in touch with him, because what he did is he looked at it and he was like, well, it's a hyperbolic transformation, of course. And he,
Is there a general recipe or? Okay.
I think from here, because I'll show you later on, like in the paper, we have this other example where instead of it being a kind of obvious functional dependence here, where applying is linear, when we get something which is like banana shaped, we call it this way, right? Again, there's a reparameterization you can do there that's pretty much, again, similar, maybe not hyperbolic transformation, but something similar, and you'll get back almost exactly the Carbarello kind of behavior. But then we have another one where it goes like this. I have no idea, there's just no way, because I think then like the particular parameterization, I have no indication as to how to do it.
Like locally, it should be a rotation, right? Like the eigenvectors of the Fisher information matrix should be the correct parameters. But then again, those are local, so maybe it's like a locally linear transformation or something.
Well, I think this comes back to what Mauro was asking as well. It's not clear to me whether or not the reparameterization does just amount to a kind of like unitary that you're applying to the Hamiltonian, or if actually, in order to get access to these, there's some additional terms that appear.
Maybe it's a question from someone. Other questions?
Yep.
I'm not sure if you can go to the slide where you have the three types of singularities.
Yep.
Yeah, so I was wondering how much we are speaking about like the first and second, of course. How much this depends on the state that you chose. And if you change the state, you keep the singularity or you lose it.
I think, well, so all of these things are calculated at the level of the state,
Okay.
right? So I think the Fisher information matrix, you're calculating the Fisher information
Yeah.
of that state. So if I then take my Hamiltonian and look at a different eigenstate, or some, that, so actually this is a really interesting point, like what George did in one of his many papers. If I look at the ground state, for instance, then I may have a singularity. But if I take the thermal state, I can lift the singularity by doing that. And it's because you're including higher orders like other states, and those states don't have a singularity, and therefore it sort of solves your problem in some sense. So there are ways around it.
Okay. For both of the singularity.
That I don't know. Like, this paper was published like a couple of weeks ago, right? So we have not fleshed out all of the details of it at all yet.
Can I ask why the type 1 do I have to rescale also the anisotrope? Isn't it just enough to rescale the lambda?
I made that wrongly. I think actually, no, I think you're right. You just rescaled the anisotropy, and I think the gamma stays as is.
Okay. Lambda and the gamma stays.
I showed George these slides. I said, I'm not saying anything stupid, and he didn't catch it. I would chastise him for it.
Yeah, just on the type 2 singularity, and you ever looked at this Hamiltonian and like when you have eigenvector, like I remember a paper with Matteo Paris discussing this where they had like they were estimating a parameter that was encoded, a single parameter in this case, that was encoded in the eigenvectors, and then they were measuring the energies. This way that naturally measurement depends on the unknown parameter.
Okay.
I was wondering if this could be an example in which you could add this type of similarity. But that's my idea.
No.
You can extend this kind of Hamiltonian to
I think this is the correct slide. I don't know if because I know George is reasonably familiar with Matteo's papers, a couple of his papers on this, and like Matteo has done some stuff in these like sloppy metrological problems.
But this one is
Older. Okay.
Yeah.
So
I can
do please.
Okay. Any other point, question, comment? If not, as Steve said, he will be around for a couple more days, and you should take advantage of his presence and come and talk to him. Let's start Steve again.